Hello and welcome. This is a tutorial for creating rigid bodies in Exudyn. And I would like to show you part of the tutorial that you can find in Exudyn in readthedocs, which is given here at readthedocs.io. And you just have to search for Exudyn. And then there is a tutorial section. So here's the start of the readthedocs, and then you go here to the tutorial section, and then there's basic tutorials, and now there is the rigid body tutorial, which I would like to show you today. There are several variants of this tutorial. So there's like the rigid body tutorial 3, which is the newest one, and it shows a quite simple approach. There are also more complicated approaches. The sketch of the model that we are going to look at is given here. It's important to see that there are two bodies with two axes of rotation. One body is fixed to ground. This is this one with the revolute joint, and the axis will be aligned to the z-axis of the global coordinates, and here is the global position 0, 0, 0, as we will see, and then there's this body aligned with the x-axis. So how can we see this? I will just zoom in a little bit. So we have here this local coordinate system of the body, and red, green, blue means always RGB, X, Y, Z coordinates. And these local coordinates and also the global coordinates are always indicated here, so you can get a figure or an idea how this looks like. And what is not drawn here is that there's the global coordinate system attached here. So let's see how we can get started. And in the tutorial, we find here all the code, and we will just copy the code because I don't have to write this, then it gets a little bit faster. The first part here is just import the relevant libraries, which is Exudyn, the utilities, which includes the interface to Exudyn, graphics data for drawing, and some rigid body utilities, which is relevant for inertia parameters and something like that. NumPy will be used maybe later on. And the first thing we have to do is to create a system which we can work with. That I will also copy. So just to have an MBS, this is what we always need at the beginning. And then what I will also copy is some parameters that I will just show in a second, which is some parameters to work with. The first thing is the gravity. So we use a gravity vector, a 3D gravity vector, which adds gravity in negative y direction. And then we have some basic length. So we have length of each of the bodies of 1 meter, a width of 0.1 meters. The body dimensions are then length times width times second width. We have a origin of the first arm, let's say this, and we have the midpoint of the first body. Now we add items. The items are bodies, connectors, loads, sensors, markers. These are the items. And the first thing that we create is a ground object. I usually call my objects, so bodies are also objects, connectors are objects, and I call them in a way that I have a starting O for object and a N for node and a S for sensor. And as it is the ground, I will use it O ground to remember this object. So I will create a ground and I will store the ID of the ground in the oGround variable. Now I will use a create function, which is something newer, which is then using this create ground. We can add a name. We don't have to, but we could use like any the fixed world basis, which is not a name for it. And then we have a certain number of variables, we could add a reference position, but as we want to put this ground to 0, 0, 0, this is the default, and we could just omit this as well. And there would be other things that we can add, like a graphics data list. Maybe we do this here, add a graphics data list, which is not done in the tutorial, but we can use here a graphics data checkerboard, so-called, which is placed at position 0, 0, 0. Normal is in that direction, and as we want to have it a little bit more in the background, we would just use a point equal 0, 0, and then put it to -2, and then the size should be 10, which means that it's a rather large one, and then it would add a checkerboard here for draw. Now we have the ground object, and now we have to create the first link. For that, we just want to add a rigid body. But in order to add a rigid body, we need the inertia. So we would use inertia defined by a function which is called inertia cuboid, which is a cuboid body having a density. Let's use a density of 5,000 kilogram per cubic meter, and the side length of this cube should be body dim, and this then gives us if we run this, I will just run this now, and then we will have the cuboid. We can evaluate it here on this side, and this gives us the inertia tensor at origin, which is the same as at the reference point, because the center of mass is here put to 0, 0, 0, and the mass is 50 kilograms. If you just take these parameters here, you will immediately get to the same value. Now, we don't want to have this inertia put at 0, 0, 0, but we would like to add an offset. This is easily possible. So to say, the whole thing is translated, and then we translate the center of mass, put it 0.25 times the length, negative x direction. And if we apply that, we can again evaluate the tensor, and then we will see that the tensor at center of mass did not change, but at the origin changed, because we now have a center of mass which is shifted. So that can be done always easily. An alternative would be, by the way, to just use the so-called rigid body inertia basis function of inertia cuboid, where we can just set the mass, the inertia tensor, and the center of mass manually. So this could also be done, but it's not done here. So you could import any kind of inertia. The second thing is graphics visualization, which is always needed in order to see what you're doing. And we will just call this graphics body 0. And now we will use a graphics data cube. It's a orthogonal cube at a certain point. So this function is a nice helper function. You can do everything manually, but this is just helping a little bit. And the center point for this cube is 0, 0, 0, which is the default. And the size is length with width. We could copy this just for the body dimensions. And the color, we can just choose any color, which is an RGB, and then a translucency, which means 1 is fully visible, 0 would be fully transparent. And in order to make this a little bit easier, we can just replace this and use predefined colors, which are color 4, means always 4 values, red plus transparency set to non-transparent. We can also add the center of mass for this body in order to see that. and therefore we add here a basis, and here we have to assign the origin, which is now just the center of mass of the I-cube 0, and then we can draw the length of these basis vectors, which is, let's make it a little bit bigger, 4 times w, and this will draw then, if we attach it to the body, a certain frame. Now we add the rigid body, so create and add rigid body, but not only the rigid body, but also gravity load, and also the node which is needed for the rigid body. So in fact, now we would have to add a node, add the body attached to the node, and add a gravity vector. And the gravity vector would again need a marker. We don't do that all, but we will do it a little bit simpler. So first, if we now look at the MBS, we would have one object, which is the object ground, which we created here. So we can also do like MBS get object. Right now, we would have the object 0, which is the ground object that we just created here. Now we add this body, and we can use here and again another create function, which is again having a name. We can omit that, and then there is a couple variables that we need. That's the reference position. So we would like to place this at the predefined position meets 0, which is at 0.5 times L, where the reference point, origin of this body. Then we have to set the inertia, which is just the inertia variable I-cube 0 that we created here. We want to apply gravity, which is the G vector that we defined. And we have a graphics data list, which is used to define the graphics. And this was the graphics body 0 and the graphics center of mass, which is the basis vectors for the center of mass. If we do that, we could run that and visualize it. So we can start the renderer, and this would now visualize everything. But as the renderer is not running in any loop, we have to use some loop. We can maybe do it in this way. This would now still not show it. We will have to do it a little bit later, because we have to put this into a according loop, and we have to assemble the system first. So maybe let's do that first. So after we have created some bodies, we have to assemble the system, and we can simulate it then. Let's do this in a very simple way. So first we start the renderer. Then we have to, so afterwards it would immediately simulate. So we can do scope dynamic with some simulation settings. And that we have to define first. So we have to add some simulation settings, which are given with default values here, and then we could add some specific values, but we don't change it here. And then we have to stop the renderer. Doing it this way and running the file, so with pressing this button here or pressing F5, it would just run and stop because it's so fast. And so we have to put here wait for user to continue, and this should now work better. And now we would see this body as we painted it in the background, and this gives us now the center of mass, the body itself, the force we see, the background. And what sometimes is very helpful we can modify some visualization settings. I will just use the general and then there's the throw world basis. And if we set this to true, then we will also see the origin of the model, which is sometimes helpful. And this would be now here. So we see the world basis. And in order to check if this is really the world basis, we can press F3. And then we see the mouse coordinates here. And then we would see that the mouse coordinates here are practically 0, 0. And here it is, for example, 1, 0 in the local coordinates. So we can change different views with Control 2, and then we can get here different views and the mouse coordinates for these different views. So this is what you can play around then. Now with Q, I can stop this and look at the model itself. What we actually want to do is we will use this maybe later. The body would now, if we simulate it, just fall down. So if we start the solution viewer, then it would load the previous simulation, and looking at that would show us that the body is just falling down, as you can see here, right? So this is not very helpful. And therefore, we are just adding a joint. And the question is how we can add a joint. There are several ways to do that. They're described at the homepage. And we will start with the first one, which is based on markers. So we have to attach markers in the conventional way. And I will just copy this one to have it in the same way as there. So I have a marker ground, which is a marker. Marker means a local position. We have different markers. We will use a marker body rigid. And this marker now needs a body number. The body number is actually what we got before. It's the ground in this case. And then there's a local position. And the local position, I would like to attach something at 0, 0, 0. The second marker is again a marker body rigid. But in this case, I use the body number B0 that I just created before. This is this rigid body, which is our moving body. And the local position will now be different. This is also visible here. So we have the model. The reference point is for the body, for the red body is here. And we want to attach a joint here, which is at minus L12, 0, 0. And this should be connected then with ground, and ground is here at 0, 0, 0. So I have to think about the local position. And this is now therefore minus 0.5 times L 0, 0. With that, I have defined two markers, and I can create a revolute joint. So I will use add object, and I can use now different approaches for the revolute joint. And one would be the generic joint, which can do or represent almost any kind of joints, which just uses two markers. I give it a list of two markers, which is the ground and the marker on the body. And now I only have to specify the constraint axis, which means which axis, which is X, Y, Z translation and X, Y, Z rotation that are fixed. So I can also add some drawing features, but I would just keep them as they are. And now I have to see, I want to fix translation for the revolute joint, but I want to let the rotation around axis Z free, and this would give exactly what I would like to have. So I can run it again. See, there's something wrong. Of course, there should be add marker, not only marker. And there is another thing. Oh, I used the small l here. This should be capital L, so it always shows me here the arrows. I can navigate here easily. It shows me the line numbers. Everything is quite an easy way to do it. And now I see that it added maybe a little bit too large drawing, but a revolute joint. And if I now simulate it, I won't see the simulation, but the solution viewer opens, and then I can run it. And then I would see, oh, it's a pendulum, right? And it will just act under gravity, and the simulation just runs for 1 second, and then it restarts again. But of course, I could simulate it all. So this works nicely. And I see that I have to do these 3 commands, and it's not very easy. So we can do the alternative way. So we will add a comment here. And this is the simple creation of revolute joint, which would do practically the same in the background, but in a little bit simpler way. And I will just use the create revolute joint function, which does a couple of things in the background. Adds markers, uses usually another joint, it's a directly revolute joint. And I can just use the body numbers here. In this case, I even don't need markers. And just use the body or ground, the P0. Then I have to specify the position of the joint. Now I have 2 options. I can do this locally in a body, in the ground, which is in this case the same, or I can do it globally. So I would sometimes prefer to do it globally. And in this case, you see that this is the standard case. Use the global frame for the definition of the local position and the axis. The axis will then be the z-axis, so it's like 0, 0, 1. You can specify any axis, and then also some drawing parameters, which we don't need to set right now. And doing that gives me practically the same. So it starts again. I press space to simulate it, and then I will see the same result as before. So following the tutorial, I can add a second body. It is described how to add it using then a second graphics object. So here are all the variants, but here's the body, graphics body 1, another rigid body, another revolute joint. And I can also add forces or torques. So that's what we would like to check here as well. So let's copy this and investigate what happens. So what we can do is we can add a torque. Let's say we want to add a torque to the body 0. The torque we will just set to 0, 0, and then let's see what happens. Maybe add a torque of 5 Newton meter around the z-axis, positive direction. There's a local position at the body which is not needed here, so we can just omit it. And we can also say if it's body fixed or not, but usually this is giving a different case, of course. If it's a body fixed torque, it will act differently. Usually the default value should be given here. Yeah, and is false, so we can just omit this from the torque. So it will be global torques and forces that we produce. Doing so, we will see the result. So it doesn't influence a lot because it's too small. So let's check what happens. In fact, it's the torque around the z-axis, which is the blue axis here. And we see that pendulum doesn't go up on the other side that much because the torque is acting against. But we can imagine as the body has 50 kilograms, at the distance of 0.5 meters, we need at least 25 Newton meters to keep it upwards against the gravity. So we will add 30. And let's trace this. I think it's even not enough because we have, let me consider this 50 kilograms, so it must be 300 because we have the gravity vector. So this should give us now a consistent acceleration in the against the gravity in the positive z direction. So this is something that we usually will not need in reality. So usually we have some torque control, and therefore we have the possibility to also add some user functions. So there is a, let me check this, user completion only works if you press the comma, and we can add a user function which we have to define before. The user function takes the MBS as argument, the time, and the load, which is in fact exactly the load vector that we have here. And what we can do now is to modify that. So we create maybe a new load, call it T, which is 0, 0, and then the component 2 of the load times now do sine of T times 10, and then we return T. Note that this is now a Python user function that is a little bit slower than running this in C++. There are also some new symbolic user functions that are much faster, and I will just add a larger load here to make this running a little bit faster. Then we can also modify the simulation settings such that we have a longer integration time, that we use the end time to set it to, let's say, 5 seconds, and then we also say the number of time steps a little bit bigger and make, let's say, 5,000 time steps, and this would give us then a nice impression how this would look like. Again, with the solution view, we can see what happens. So the load is now sinusoidal, and it's increasing and decreasing, and this is what we know. So it's accelerating and braking the system, and that's why it is driving into one direction because of the initial velocity it gets. Okay. So we could use a cosine here and turn off the gravity. Then we would see a little bit different behavior, I expect, just for you to see that. So then we would see that it accelerates and goes back again. And this is with the different. Of course, you can do every kind of loading, and you could also couple it back to some current states. So you could also say here mbs dot, and then read some sensor values or get a node output, it's called, which would give you some data about the current status of the system, and then you could create some control loops, which have to be considered with care, but it would work as well. And we would maybe like to see what is coming out here. So we would have the sensor, and we just add a position sensor, the very last step here, which is also very simple. add sensor body, as we want to attach it to the body. The body number equals B0. Then we have a local position that is now at the end, which is at the tip of the beam that we have here. And we then can store this internally, which is not the default. It would also otherwise be written to a file, which we have to prescribe here. And we have the output variable type that we have to specify, which is the type of thing that has to be measured in the body. So it's measured for body B0 at this position, stored internally, and then we have an output variable type position, and it would then store the position of this body, of this local position. If we run it now, again, let's turn off the solution viewer, also turn off this weighting, then it would compute that, and now we have to start the visualization. There's the plot sensor feature, and we just can use it this way and just run this line by pressing F9 in Spider, and this would then, if everything is installed, we need matplotlib for this, it would show us the position of the of this pendulum. This is now the X position. I have to change this and have to show all the components. So let's draw the X, Y, Z position, and then we see the Y position, which is more interesting, which is then going from 0 to 1, which is going upwards. The X position is going from 1 towards 0, and the Z position is unchanged. So this you can use to analyze, but of course you can export this data then to the file as well. So with that, I think I showed some introduction to the simple dealing with rigid bodies in Exudyn, and we created the basic variables to describe the system, added a ground, inertia, graphics for the body. We add a body, either the gravity or adding a torque. We have several ways then to add forces or constraints, joints. This is done easiest with the create functions, with create revolute joint. We added a user function for a torque and a sensor to measure the output, and in the end we simulate like always with solve dynamic here with the renderer started, and this gives a very nice model of a pendulum, but you can extend it to any kind of machine. See the tutorials and further examples, so that if you like to see more about the rigid bodies with the create functions, just search for create rigid body. Also ChatGPT knows about it, by the way. I gave it some hint. There's the tutorial, but there's much more examples, so you can find them here in the example sections. And if you just open one of these examples, there are some of them maintained very nicely. For example, the stiff flyball governor should be in a good shape, where you would find a description of a much more complicated system, which is using the old style of markers and joints. And yeah, with that, I would like to thank you for joining and watching this video, and see you next time. Bye bye.